Hey, Honors Physics students, this is what you've been waiting for, the Chapter 7 and 9 textbook hints. Starting at page 190 to 194, the assignment for Chapter 7, this is primarily about gravity and the effects of the force of gravity. So for instance, let's look at number 54. Remember, the best way to do this is to have the book in front of you, look at a particular problem, push pause while you solve it. It seems to me the idea is to be working on the problem at the same time as you see my hints, but however you want to use it. Look at number 54. It asks you to find the force of gravity that the sun exerts on Jupiter. Well, if you look back on page 173, you'll find a table there that will help you find the mass of Jupiter, the mass of the sun. What you need to realize is capital G is the universal gravitational constant. And we talked about that in class, and it's in the book. It's always the same, 6.67 times 10 to the negative 11. What you need to realize is the most common student mistake is to forget to square r. R does not stand for radius. It stands for the distance between the center of the two objects. So I didn't list anything here for number 55 because it's the very same formula. This time it's the force of gravity between two people. Again, m1 will stand for the mass of one object, m2 for the other one. R, not the radius, but the distance between the two objects. Let's look at number 60 next. Number 60 is about a 1 kilogram mass, weighs 9.8 newtons on Earth's surface, and they give the radius of the Earth. Calculate the mass of the Earth. And for part B, you are going to calculate the density of the Earth. So a couple things to look at. Certainly, on the first part, if you have a 1 kilogram mass, and you know the weight, and you know the radius, why not use the very same formula to find the mass of the Earth? The mass of the Earth becomes one of the masses. So part A should be pretty easy to do. Part B uses density equals mass divided by volume, a formula you had in chemistry. And then also very useful to know the volume formula for any sphere, like the Earth, would be 4/3 pi r cubed. Hopefully number 60 will be more successful now. Let's look at number 64. Number 64 is two spheres placed so that the centers are 2.6 meters apart. The force is given. What's the mass of each sphere if one is twice the mass of the other? So I think you're getting the pattern. It's the same exact formula. This time we have an unknown mass, and the other one is 4 times the mass. So when you use the formula, call this one m, call this next one 4m. I think the solution will be pretty easy to arrive at. Now let's look at numbers 71 and 72 on page 189. Or 71 and 72, which is on page 192. But if you look back on page 189, you'll find the satellite speed and the period that it takes for an object to move around the entire Earth, and the acceleration due to gravity, lowercase g. So the hint on number 71 and 72 is to use the formulas you will find on page 189. Okay. For number 72, use one little hint. Weight on the surface of a planet is m times lowercase g. I think that'll help you. For the final problem that I'd like to help you with on this chapter 7, would be number 84. So I'd like to look at number 84. You'll find number 84 on page 193. And number 84 says if you weigh 637 on Earth's surface, well, take a look here. If you know the weight, you should be able to divide by g, which is 9.8 on the Earth's surface, to find the mass. Then you could use the general force of gravity formula to find the weight or the force of gravity on Mars. This is a good hint. Utilize that hint. Chapter 9 is primarily about momentum and impulse. I have to switch from chapter 9 to page 251 to 254. First question, 56, 61. Take a look at 56 and 61, where they ask you about the amount of time. On 56, it's about golf. 57, It's about baseball. 61, about volleyball. These are sport things. You're starting to get the impression that we use this a lot in sports. Impulse is force times time. Change in momentum is m delta v. This is what you use for 56 through 61. All those ones in there. That's what you use. Number 66 is the same exact thing. You use impulse equals change in momentum. However, the impulse cannot be force times time because the force keeps changing. Use the area under the force versus time graph. That will give you the entire impulse, which you could use to help you solve for the change in momentum and the velocity. That's enough of that one. Let's try just a few more. Let's look at number 74. Number 74, you're going to have to switch to page 252, I believe. And this is a collision problem. If you have a collision problem, you are going to use our most important formula for the unit. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Remember, the prime means after the collision. And that would be, I'm sorry, that's number 74 and 76. That's number 74 and 76. Number 84 is, again, back to finding the force times time equals m delta v, because this is called the impulse. Remember, the force times time is the impulse you give, and this is the change in momentum. And the last thing I want to look at is number 85. 85 is the dragster that has a change in momentum. Remember, all of these are assuming newtons, which means kilogram, meters, and seconds. So number 85 is pretty easy to do if you remember to change so that everything's in kilograms, meters, and seconds. I think that'll help you a whole lot. Thanks.